Okay, this means we are now able to get going. And so before we go into doing MATLAB simulation, I briefly show a few slides that show us the kinetic data on which the model is based and sort of motivate why we are looking at this at all. And I'll explain a couple of features of this reaction. So we're looking at one reaction only to make things simple, similar to what you did in the toggle switch model. Looking at one reaction that's supposed to happen during glycolysis, during the glycolytic flux, and it's the reaction that is catalyzed by the enzyme phosphofructokinase. So it's one of the regulatory enzymes. It's supposed to be a key enzyme, but what it does is basically taking a phosphorylated sugar, a 6-carbon sugar, and converting it into a biphosphorylated 6-carbon sugar. So in this case, the standard textbook case, it takes fructose 6-phosphate and phosphorylates it to end up with fructose 1,6-bisphosphate. So that's the reaction we're going to look at, and this has been studied in vitro, and in vitro kinetics give us the results shown on the second slide here. What we have plotted on the horizontal axis, the concentration of ATP, because as for any of these kinases here, ATP is also a substrate. It's not only taking the sugar or the sugar phosphate, but it also needs a co-substrate, but it's a second substrate, right? So we can do kinetics with respect to this second substrate. And when this was done in 1982, there was a big surprise that ATP is not only a substrate in the conventional sense, but it's actually a substrate that has some peculiar regulatory feature. If you look at the curves, for example, the bottom one that's related to zero concentration of a certain key regulatory molecule that they add later on, which is the content of the paper, what you see that while ATP concentration is zero, there is no reaction, which means it's an essential co-substrate. For small concentration of ATP, the rate of this phosphofructokinase reaction will just go up, as you would expect for any, say, Michaelis-Menten kinetics. However, in all three cases plotted here, following a certain maximum for even higher concentration of ATP, the reaction rate is found to drop again. And that means that although you put very high concentration of one of the substrate, the reaction is actually slowed down. And you can see in the curve that is interesting for us, namely the bottom curve, this rate drops nearly to zero, which means the flux through this enzyme is essentially shut off. There is no conversion of ATP and fructose 6-phosphate via the phosphofructokinase, and specifically this is for isoenzyme PFK1. So this is what we keep in mind, and this is what we're going to model. However, compared to previous modeling approaches that we have done in Module 1, we are now looking at the model that supposes to mimic in vivo open flow conditions. So the model scheme is somewhat extended. So in addition to having our enzyme reaction at the center of the model scheme that is shown in this slide between ATP and ADP, we have three more processes that come into play. Namely, there must be a source of ATP, which is the arrow pointing to ATP. There's an influx of ATP from somewhere. It's not shown by which process. It might be diffusion, it might be something coming from the mitochondria, or by some process, by some synthesis process. But there must be a source of ATP, otherwise any reaction will just end up at zero amount of ATP. This is not the case in vivo, but to avoid it also from accumulating, there's an outflux of ATP into somewhere, into say another compartment, or there's a reaction that consumes ATP because there are many other kinases present in the cell. And finally, we have an outflux for ADP to prevent it from accumulating as well. So given this scheme, we then see at the bottom of this slide the reaction equations. So we have two differential equations, and there are two ordinary differential equations, one for each of the reactants that interest us. First is ATP. So we have a derivative for dATP over time, showing how does ATP change over the course of time. And on the right-hand side, a couple of terms. Second rate equation for ADP, similarly, how does ADP change over time? And on the right-hand side, a couple of terms. So the number of terms is equal to the number of black arrows for each of the components in the upper scheme. So there's 3 terms for ATP and 2 terms for ADP. And you can see we have a term called A, that is a constant influx to ATP. We have minus B times ATP, a first order reaction going out of ATP. And similarly below, minus C times ADP, a first order reaction going out of ATP. And then on the right hand side in both equations, formulated as if mass preserving, is the rate expression for a control of the rate catalyzed by phosphofructokinase 1 in a way that is reminiscent of Michaelis-Menten or Hill equations that we have seen previously, but we're going to play with those two little things that are there, N and M. These are the exponents put on the ATP concentration in that expression, which will allow us to model the forward inhibition shown in vitro. So this summarizes our introduction, and when we now go to first study this nonlinear function on the right-hand side, then going to look at the steady states and the vector field of this whole model, and finally doing some simulation at the end of the session. So I take this slide away, and because we need space for the MATLAB, I also stop showing our faces on the video camera, and if I hand over to Rob, will now be able to start with our first exercise, which is on the Hill function with those specific coefficients that we have highlighted before.
So hi everyone. So you want to have a look at this Hill function again, mainly to see what happens when we have different powers on the top and the bottom of the fraction. So if we start by defining the Hill function as a MATLAB inline function, so some rate, say v, is equal to the @ symbol, which denotes we have a function, and inside the brackets we need to put the inputs to that function, as we've seen previously in these sessions. So we know we've got the concentration of ATP, we've got the Vmax, we've got Km, and then we've finally got the powers N and M. And then the form of this equation, we can copy that from above. Okay, so this is an inline MATLAB function that defines just the Hill function part of the differential equations that we saw previously, function of ATP, Vmax, Km, N, and N.
And our goal in this exercise is to find out what combination of N and M will actually give rise to a kinetics as the one observed in vitro. So we're looking at a model of in vitro kinetics.
Okay, so let's first, we want to do a new function, a second function, where we parameterize this existing function. And let's do that simply by assuming N and N are the same, and they're equal to 1. So I'm going to have V1 is a new function, which now only is a function of ATP. We want to call the original function, and we want to say we still want to know ATP. And these values above are going to give me the numbers I'm going to put into this function. So you can see Vmax is 0.5. So the second argument to this function should be 0.5, and similarly 0.1. And now I'm also going to set N and M to 1, as I just said previously. So we can see what this looks like, just to remind ourselves what the Hill function looks like. And then, of course, we can plot using the fplot command. So pass the function, give it the limits, and let's just give it a color, so R for now. Okay, so if I run this file, okay, I hope you can all see that. So we have one curve, starts at 0, 0, and goes up to nearly 0.5 at 5.
So what does this curve show us now? It shows us that for increasing ATP concentrations, so as we go to the right on the horizontal axis, the rate of this reaction modeled by this expression where n and m are equal to 1 is just increasing. It's increasing hyperbolically, as we call it in mathematics. And so this is nothing but a Michaelis-Menten expression. And it does not correctly reproduce what we have in the kinetic data, because kinetic data show that the rate decreases for increasing substrate concentration, in this case ATP.
Okay, so we've got a hint already that we want to try setting n and m differently. So you can see here in the parameters it says n equals 1 and m equals 3. So how about we try that?
Yeah, the reason these numbers are there is that how the model is set up for you in a model function file. So if you look at the downloadables from the materials page of today's session, you will see there's a model file, and it's the parameters are taken, just copied over from that model file. So why would we actually look at something where m is larger than n?
We want the component on the bottom half to get bigger quicker.
Right.
So
what we want to have is that for very large concentrations of ATP, we would like the rate to go down. So means we must have something that the larger ATP is converges to 0. And for a fraction to converge to 0, it always means that the denominator gets very large. And if you ever remember how a Hill function works, a Hill function is the case where n and m are always equal but larger than 1. But in this case, there is no conversion to 0, but there's a convergence to Vmax, just as in the Michaelis-Menten. So let's take a look at what if we make the power of ATP in the denominator larger than the one in the numerator.
Okay, so I'm going to go back to this function. So down here we've got v1, and now we need a v2. And the only thing I'm going to change is the final argument, which I'm going to change to 3. So that's setting m equal to 3. And now if I do hold on and a second f plot, maybe let's make this black, call v2. Hope you can see this. I'll move it a bit. So we should have two lines now, one plotting with m equals 1 and one plotting with m equals 3. Okay.
So the output now, additionally to the previous one represented by the black line, is different, and with these settings, which we have sort of pre-tested, does show, at least in some qualitative sense, the desired behavior. Namely, there's an initial increase starting from 0, the rate goes up to a value, in this case is 1.2, but it's an arbitrary value. But the function, this nonlinear function, goes to a maximum, after which it starts to decline, and following an inflection point, it has an exponential decay down to 0. So this is in some sense what we wanted to have. We have a way of modeling this in vitro kinetics, which correctly represents the qualitative features of substrate inhibition, as we call it. Inhibition because the value for large substrate concentration is below the one expected for a Michaelis-Menten type of increase. So we have this inhibition by ATP as it gets higher, and we can use this form of the function as we have derived it now to put in our full model that mimics the in vivo situation. And maybe there's a comment in place that, as you can see, we have now used our knowledge of how fractions that involve exponents work. Right, so we have said that because we want the concentration to drop, or the rate to drop as concentration increases, we have made this m coefficient, this m exponent, larger than the n exponent. So this is not strictly a mechanism. We have not implemented a mechanism. So we shouldn't call that a mechanistic model, but actually an empirical model. However, if you check with the literature, for example, on the Hodgkin-Huxley equations, how Hodgkin-Huxley modeled the action potentials in a nerve cell, you will see that what they did is exactly the same thing. So they had some mechanistic approach taken from Kirchhoff's laws on how current and voltage are related, which they thought to reproduce the action potential, but they actually measured some data and they empirically fitted the shape of the nonlinear function to account for this data shape. And so we have done that here. And so this combination of exponents n equal to 1, m equal to 3 is what we are going to look at now in a model of the in vivo open flow system. So I think we are finished with this first exercise and we can take this figure away and also the script file away. As mentioned previously, the worked out code is actually there in the script that you can download from the materials. So let us now go to the analysis. The analysis has a second template prepared with a little bit of text included to make it easier for us to show you how it works. Specifically, what we are not going to do, we're not going to go through the details of how to plot a vector field. For the vector field, we have pre-prepared a script file, which is shown here, which says calculate and plot the vector field. It's all pre-prepared, equations are in there, parameters are defined. But if you want to understand it, it's just equivalent, it's just written in the exact same way as the one for the toggle switch in the materials. So the only thing we have changed is we have replaced the equations with our current model, which has the input and output to ATP and ADP according to the PFK1 kinetics. So the first thing we can plot, however, with this script, our vector field. Rob, how can you do that conveniently?
Okay, so all we need to do is actually just call this script from our new script file. I just wanted to point out very quickly that this is just creating a grid over which we're calculating the direction of the derivatives. So we should expect to see some sort of field of arrows in the plot we're going to see in a second. So all I need to do in this new script is call that the name of that file, so vector field. Okay, well, I didn't find it for me very quickly. And if I click run, there we go, that's our plot that we were expecting. So if I just make that a bit bigger.
Okay, so we have the vector field plotted, and there's a couple of things to say before we go further. So you can actually execute this script from another script. So it's called a script from within a script. It's what we have done here by typing its name and executing that code. So it ran immediately.
And that's exactly the same as if you wanted to run a script in the main MATLAB command line.
You could also type the name into the command window of the MATLAB and have it produce the same figure. So let's take a brief look at what we are looking here specifically, and this is to be our theme for the rest of the session. This is a specific plot, namely one that has on the horizontal axis the concentration of ATP, our co-substrate or our major substrate for the PFK1 reaction. And on the vertical axis, we have the concentration of ADP, so the product of this reaction, which means we have no explicit time here, and we have not plotted any of the parameters. And this kind of plot is called a state space, which is the major topic of this session.
It's also called a vector field.
And the little arrows here pointing us to what is called the vector field, namely in which direction is the change going to happen for any combination of these two concentrations.
Or a phase plane, it's also called. So each of these arrows denotes the direction that the derivative or the rates would take if they were started at that point. So as Gerald said, there's no time on this plot, but by following arrows, you're implicitly following a time course.
Right, and if we can just roughly see, I don't know how big that is on your screen,
Okay.
what we can roughly see that over a large part of this figure, say from an ATP concentration of 1 onwards to the right side, all of the arrows seem to have a tendency to go down and to the right. So apart from the very far right at 10, they seem to go only down, but all the other arrows seem to have a tendency to go down and right, which means there would be a tendency to evolve towards that value of ATP equal to 10. But on the other side, you can see that this is not the only behavior, that for small ATP concentration, specifically those that are smaller than, say, 0.5, the arrows tend to point upwards and more to the left. So that means there's another tendency of evolution which is now already indicated by this vector field and which we will find out to be related to the fixed points that exist in this model system.
Okay, if I make that a bit smaller again. So you can see that our next task now is to calculate something called a nullcline. So that's a line in this vector field, in this state space, where something is equal to 0. In this case, we're going to look at the rate of change of the concentration of ADP with respect to time and see when that's 0.
Right, so there's actually, as you have seen in the materials, for a system of two differential equation, if it's a fully coupled system, means that each variable also affects the other variable, we would have to calculate two nullclines. You are asked to do that in the toggle switch model, for example. However, we have a bit of a specific case here, because what we want when we plot the nullcline, you can see we want to have a graph in the state space on the left-hand side. And in order to do that, we need to have ADP expressed as a function of ATP, whatever that function then is. However, if you look at our first equation, there isn't actually any ATP involved. This first equation is independent of ATP, so there's no nullcline to be calculated here. However, it is possible to calculate a nullcline for this second differential equation when it is set equal to 0.
Okay, so this is just a little bit of rearranging. So if I just make a comment here, what effectively we want to solve is this equation. So minus C times ADP plus this Hill function we saw before is equal to 0. Of course, all I have to do is rearrange by taking that component to the other side and then dividing everything by C gives me the answer.
Let me just see if I can follow it also. So you have minus C times ADP is the first order rate term that contains the concentration of ADP, and you have put that on the left side by multiplying it with minus 1. So it turns out positively as C times ADP on the left-hand side. And in order to get rid of this factor C, you have divided both sides by C, which leaves a 1 times ADP on the left-hand side, which is just ADP. And on the right-hand side, we have this nonlinear rate function from before divided by this constant C. And C, we have defined it before, so its value will just scale this function.
Now we have one variable in terms of the other. We have a function that will let us plot our nullcline. So first of all, I need to convert this into a MATLAB function. So I'm just going to call this nullcline. Oh, actually I'm not, because I'm worried that MATLAB might have a function that's already called nullcline. So what I'm going to do is call this f of nullcline. Oh. Sorry. And we have a function, so an @ symbol, and it's a function of ATP. And we can take the function from here. Okay. Now, Gerald, in that function vector field before, did we explicitly give values to Vmax?
Yes, sure. We had the values that are already defined. They should be in our workspace. If you want to check, I think it would be possible to see them in the workspace and see what is Vmax is 0.5. So all the values should be there.
So that's why we don't have to. Define them again, or define them in terms of our function, because they're already defined in our workspace. Okay, so that defines our function. So all I need to do is now plot this, but of course you want to have this vector field stay, so I'm going to do hold on. Use the handy fplot function again, call this f nullcline function. Give it the minimum maximum, which we know for our ATP to be 0 and 10. And let's call it R. Let's color it R, red. Okay? So let's try running this. Great. So I can't quite see that, so I'm going to make that a little bit thicker. So hopefully you can all see that. Okay. Great.
So let's take a look. Let's try a quick interpretation and see what this tells us. So within that vector field, we have now a line where we know that whenever you are on this line, the rate of change of ADP is equal to 0. So what that means, that vectors that actually start from on that line should be horizontal. Horizontal meaning that the ADP concentration from that point onward will neither increase nor decrease. So if you see a vector cutting that line and not being entirely horizontal, is because the start of the arrow is not on the line. But if it starts on the line, that's how it's defined, then the evolution will be such that it doesn't change ATP. It doesn't say anything about the direction in which it goes. It might go to the right if ATP increases at that point, or it might go to the left if ATP decreases at that point. But ADP will be strictly 0, means zero derivative, no change, and a horizontal vector in that point along these lines. Which also means that, of course, or any fixed point that we find in the system will have to be on this line, because there's the fixed point condition is that both variables don't change over time, but also, of course, that the ADP variable doesn't change over time. So any fixed point would be expected to lie on that red line, which is now plotted. So it gives us information of how this vector field is structured in some sense, namely telling us all the situations where ATP vector is horizontal. Okay, having this, we can now actually try to find the fixed points. Where are they? How do we do this?
Okay, so if I make this a bit smaller again so we can see our script. Okay. Well, we've already prepared the next section. At least we've added the equations, the differential equations that we had described previously. So a function of x. So now x is actually an element with two things in. It's got the concentration of ADP in the first component and the concentration of ATP in the second.
The other way
That's
around.
the other way around, sorry.
It's ATP in the first line.
Because we're converting ATP to ADP, sorry. So yeah, so ATP and ADP. So that's the only difference with the way we've described this previously.
Right, so previously we had written it as two entities, one called ATP, one called ADP, but now they are put into one vector. It's the vector called X, and this vector has two elements. The first of which is ATP, or representing concentration of ATP, second of which represents ADP. Otherwise, constants and terms are identical.
So we want to solve this equation for this find steady state, so find where it doesn't change. So we need the solution to both equations when they're equal to 0. But this will depend on the initial concentrations of both ATP and ADP.
Yes, because that's a numerical way of finding the steady state by an iterative scheme. And any iterative scheme mathematically, just as in simulations, needs a starting point to be given to know where from the iteration should start. So it's, I think, a rough Newton integration here. But let's take a look.
So I'm going to find a first point, so P1, and then I'm going to use the fsolve function. I'm going to give it the function f, and I'm going to give it our initial conditions, so 0.2 and 0.1, say, to start with. Okay. I'd like to plot these on this plot we've already started. So if I hold on, I'm going to use the scatter command and call the first point, the first number in the first point, and the second number in that point. Give it, is that a size command? 200?
200 is the size of the symbol that's plotted in the scatter plot.
Just say black for now, and also we want filled elements. Okay, so if I run this. Okay.
Right, what can we see? There's an addition to our plot now, and because we had the command hold on executed once before, what we can see is that for an ATP concentration of, it's hard to guess, 0.2 or 0.3, and an ADP concentration of 4.9, so close to 5, a dot was added, the filled black dot in the scatter plot. And this is now one of our steady states. So we found one of the steady states from a certain initial condition, and as expected, it's on that line. And what does steady state mean? If we look at the arrows in its immediate neighborhood, and you have to have that on your screen to maybe blow it up a little bit, then the arrows that are in the neighborhood of that steady state should actually point towards it. So if everything was right, and if you would do it with high resolution, the arrows, the vector field around the steady state pointing to it, which we could do by zooming in.
Okay.
And remember that the arrow always doesn't necessarily go to where the tip of the arrow is, but it shows the direction that it has from the base or from the start of the arrow. Okay, can we have that?
I'm going to zoom back out again a bit.
And we have the original plot again. And so with the steady state information, you can see what that predicts. So biologically, what that means, we have an open flow model. So like in the toggle switch, what we're expecting is that in the long term, the evolution of the model will predict us a stable steady state, means stable concentration, which is a measurable thing, something that we could check by measuring, say, for example, this case ATP. If we had means to either take a sample and measure its ATP concentration or do it in vivo, then we could confirm or reject whether the steady state in the experiment is actually equal to the one that we model in this open flow model. What it means is that we have a very peculiar combination, namely we have a situation where the steady state consists of a very low concentration of ATP, means there's very little ATP present in this case, but a fairly high concentration of ADP. And similar to the toggle switch, that will be complemented by another steady state existing at other values of ATP and ADP.
So just quickly show that. So our point 1 was generated from a certain initial condition. Now if we change the concentration of ATP to say 0.5, again duplicate the plot command. But let's now say this one's blue. If we run this, okay, so we can see because we've had hold on a few times, we've ended up overplotting various bits. But we can see there's now a second dot that's actually on the other side of this hill.
Right, and now the peculiar thing about this second dot is if we now look at the vector field in its surrounding. And you can see there's a couple of arrows, each of which has one very, very peculiar feature, namely that the arrows seem to point away from that steady state. So means that whatever you do, if you come by some incidence, if you come to have a concentration ratio of these two that brings you into that neighborhood, then any evolution will show that you will tend to go away from that steady state. So there's nothing that will be asymptotically stable. So if you, for example, start slightly on the right side of the steady state and follow the arrows that are in that region, you will see that the tendency will be for ATP to increase. The tendency for ADP will to decrease. Conversely, if you are on the other side of that steady state, and I've just put my mouse cursor there with the minus sign, you can see following the little arrows in its neighborhood, ATP will actually increase, if not a lot, but a little bit. However, ADP will increase. However, ATP will now decrease. So we have an opposite tendency. So it means this point is a special point that is not something that we expect to be observable, but it's a state that actually forms a decision point. A state that decides if you are on the left side of it, you will have an ATP tendency to go down, decrease ATP concentration. If you're on the right side of it, have an ATP concentration tendency to go up. So this is something that interests us because while we might not be observing it, is of course determining the eventual outcome of the experiment. And this is the crucial feature of bistability. If we just recall the decision, bistability is defined as a setup of a system in an open flow environment where under the exactly same parameter settings, two different macroscopic states are being observed. Two different macroscopic states may be observed. In this case, one state with a high ATP concentration or one with a low ATP concentration.
Okay, so I'm going to close this for now.
Okay, we leave it for everybody else to find the third steady state, to give a good initial guess to find the third steady state. And of course, the idea is if you want to find a steady state with high ATP concentration, you make the initial concentration to find that steady state fairly large. And the number 10 in ATP concentration was a good initial guess. So if you want to try it, you'll be able to use this exact code, slightly modifying it, and also find the third steady state.
Okay, so I'm going to close this script and I'm going to open a new script.
Our final script for today is called, it's a final analysis script, is called eigenvalues. You can get it from the template. And what is easy here is that the equations are already written in it. But what is interesting about this script here?
So we found some steady states, but we actually want to know the stability of them. So we want to know whether they're attractive or repulsive.
Right, because we have seen already that there's obviously two different things, and we know that from the toggle switch already. But there's actually a strict way of characterizing these steady states, and that's what we are going to do now.
So we've defined the same equations again, now with these differently named parameters with an S on the end, just so that MATLAB doesn't think they're the same parameters as before. And the reason we want to do that is because we now want to use symbolic parameters so we can later specify exactly what these numbers mean. So F is equal to the rate of change of ATP, and G is equal to the rate of change of ADP.
So why does it say U and V now?
So U is the concentration of ATP and V
right,
is the concentration of ADP.
actually taken from the script for the toggle switch where U and V were employed. And we leave that here as U and V to not confuse things by calling them ATP or ADP again, because that might lead to error messages. And it's for beginners, it's fairly hard to debug those error messages because we found them frequently with our students to be fairly incomprehensible, to be fair. So we give them new names, but remember that ATP is now represented by the symbol U, ADP concentration by the symbol V, and all constants are named as before, but have an added S to denote symbolic, so that they are not being confused by MATLAB. Because we want to leave the previous things in the workspace, we actually need to access the value of the steady state to evaluate.
So we know the next thing we need to do is calculate the Jacobian of these equations f and g.
What is the Jacobian? So we need to remember it's a very abstract thinking that comes into play here, and it's not very easy for beginners to understand. But the only way to get used to it, to use it a couple of times or to use it with different models. Jacobian comes from actually from a Taylor expansion. So if we look at it mathematically, it's a sort of called linearization of this matrix. What it is composed of is partial derivatives. So those who have done the previous session, session 3, know how to do partial derivatives. And that's what is used here in the calculation of the Jacobian. Calculate from the rate equation the two partial derivatives with respect to first ATP and then with respect to ADP, which gives us a 2x2 matrix with 4 elements. Conveniently, MATLAB can do that for us without us having to do the partial differentiation by hand.
Yeah, with just the Jacobian function, which is very handy. So we need to give it the f and g in this form, and u and v as well.
So we first put in the two equations, which are called f and g. These are just the rate equations as defined by our model. And u and v are our two variables. So that means both equations with respect to both variables is the convention now that the function Jacobian expects in order to work properly.
So we want to be able to pass our value of the Jacobian, the parameters that we had previously. So we're going to use the ever handy MATLAB function to convert the symbolic function into a function that MATLAB can take arguments in MATLAB. So all we need to do is pass it J. Okay.
Right. So maybe we only do it so far. We see whether the Jacobian in its symbolic and in its algebraic form can be found.
Okay. If I run this. It's taking a little bit of time. Great. So it has. So it's found a solution. The f of the Jacobian as our function. It's this thing, which is not very nice. Luckily, we don't really have to worry about that, do we?
It's a very complicated thing, but there's one thing that we definitely need to know, and this is
it's the order.
This function now contains all of the variables and all of the constants. And if we want MATLAB to now work with this, we need to remember what order these things have. So you have now copied that from the command window into our script, but you have commented it.
Yeah.
Where is it now?
Sorry, I've just moved around some of the things. So first of all, we converted the symbolic Jacobian to an algebraic function.
So fj is our algebraic function of the Jacobian. This is what we want to work with.
And then we've checked the algebraic function for the sequence of parameters.
And we've done that by looking at it fj in the command window, and it says if we don't suppress the output, and it tells us that this function takes arguments kms, vmaxs, bs, cs, ms, ns, and u only. So means v is missing. We don't need to provide a value for ADP. Also missing is a. We don't need to provide a value for constant a. Why is that? Well, if you remember, we're doing differentiation. Each of the terms comes from a differentiation. A constant term, a constant additive term, drops to zero by differentiation. So that's why these things are not there. Also, ADP is not present in the first equation, so we have no entry for this, and we don't need to provide it in order to evaluate our Jacobian.
The other important thing is here it tells us the order that we need to give the fj the parameters in.
Right.
So if we want to call fj now, which I believe is our next step, then we know explicitly which order to give things in. So we need to calculate the eigenvalues, but first of all I just want to call the right fj. So fj, so we know we need km, we need vmax, we need b, c, m, n, and u. And the value of u that we want to give it is the value of u at the value of ATP at the first steady state, which we had was P1, but it was the first element of P1. So this is what we calculated just in the last script file.
But shall we check whether it's still there? Is P1 actually still there?
It should be.
P1 is there. And so we have values, the first one for ATP and the second one for ADP, which we don't need because V is not there, but U is required. So this value of 0.2152 in our command window on the left-hand side will be needed to evaluate the Jacobian at this point. So it's now calculating what is happening at this point in state space.
So if I just run this quickly to show you what the output of this is, we have a 2x2 matrix, which is what we expected because we have two functions and two variables. But we're actually interested in calculating the eigenvalues of this Jacobian. And so MATLAB gives us the function eig to do this. Okay?
Right, so now we know what the Jacobian at the steady state P1 is, which was our low ATP steady state. And if we want to look at what is the stability of this steady state, of this first steady state, then we can use the eigenvalues to find that out. The convention need to go to the materials to find it out, but let's see what the output of this call is when we actually get it. So if we do the eigenvalues now at this steady state, and we have an output which is two numerical values. One is minus 0.2 and the other one is minus 3.4. What does this mean?
So if they're both negative, we have a stable node.
Stable node. So you need to look it up in the materials how this comes about, but just briefly, this comes from the assumption that in the linear system we can actually solve the differential equation analytically, and that we have exponential functions which are decaying if that value is negative. So if both values are negative, means we have a state that is attractive in the sense that all initial conditions that start in a neighborhood of that state will tend towards that steady state, meaning that it will be a long-term stable state.
So we had the second stable state, which we should still have in MATLAB's memory, so P2.
We can look at the eigenvalues also evaluated at this second state.
Just call it something else and give it P2 as our value for U. If I run this,
the situation is now different. The numerical output shows that we have one negative value, minus 0.2, and we have one positive value. And if you look back into this, positive value means that there's an evolution away from this steady state. And an evolution away from it means it is an unstable state. It cannot be observed. And so this is consistent with our previous observation that this second steady state, the central steady state, is actually a decision point rather than a stable final state that would be a measurable value.
So that's an unstable saddle node.
And it's called a saddle. These nodes, these steady states that have eigenvalues such that some of the components are stable and some of the components are unstable, is called a saddle point. Okay, and with this we conclude our analysis, and we have a few minutes left. We might just do a simulation, maybe not too much, but we might just look at the transition from some initial state to the steady state by looking at our model and numerically integrating it. Now, as you have all done this before, should have done this before, best thing is to not explain it, but tell you that we have prepared the model file and everything is written in there with the parameters that we have used so far. And Rob will just write a line of code that executes this model by calling it with the ODE45 solver.
Okay, I'm just going to quickly define some initial conditions, 0.6 and 0.1. Just set the parameter A to be 1. What's the parameter A, Gerald?
Parameter A is the constant influx of ATP into our system. So that's a source of ATP, which is supposed to be providing ATP at a constant rate. So of course, that's a lump parameter, which means from wherever the ATP comes will be lumped together in this one process. And to have it constant, it's of course a matter of convenience. There's no such thing as saying that this will truly be a constant rate in vivo, but it's a simplifying assumption that helps us to deal with the model easier.
Sorry, I'm going through this so quickly. We've not got very long left in this session.
Okay, because we are at final time.
I just wanted to add the reason we had to define A here is that our model defines A in the definition here. So as well as time and our on our concentrations, we also have a value A defined in the definition of the function file, and it's not defined in the parameters. So that's why we need to define it separately for ODE45. Okay. Oh, I've missed one bracket off. So if I run this now.
Okay, so the outcome of our simulation shows us that with these initial conditions that we have here in this model and this parameter settings, the prediction would be that the ATP concentration drops down to a low value. And remember from the previous steady state analysis what this value approximately is. Whereas on the other hand, the ATP value starts to rise until it reaches a value close to 0, just below 5. Sorry, not 0, just below 5. So we have high concentration of ATP finally and low concentration of ATP finally. This situation will change with a slight change in initial conditions.
So changing 0.6 to 0.7.
So if we run this simulation again with a slightly increased ATP concentration, and the ATP concentration changed, we knew that before from our steady state analysis, it's now past the value of the unstable steady state, of the unstable saddle that we found. And if you compare the two graphs, what we have as a final outcome is that with slightly different initial conditions, we have a different macroscopic final state. Although all parameters are being kept the same, just having a different history, namely coming from a different initial state, leads us to two qualitatively different, macroscopically different outcomes. And so if you have such a thing measured in an experiment or in vivo, it might not be something wrong with your experiment. It might actually be that you have discovered a case of bistability.
We can also see a switch between bistability if we perturb our system. So this perturbation requires we change our initial function fail to have an extra term, an extra if statement. So if t is less than, say, 50 and greater than 50 and less than 70, let's set our a to 0, an end. Otherwise, A will be as we set it in the simulator.
So what does this mean? We make a simulation up to time 50 with A as set in the script, and then suddenly we drop A to 0, means we assume that for a period of time, in this case 20 model time units, we have no supply of ATP, means we expect the ATP concentration to drop, right? And if we start with a value of 0.7, we will know that we start with the high ATP state, and then if we stop supplying ATP for some time and leave it long enough, let's see, the final simulation following time 70 is then resuming the old parameter sets as before. So what we have here is, let's just concentrate on the blue curve. We have an outcome that shows that in the range from 0 to 50, we have an increase and nearly saturation at this high ATP steady state. And then when the supply stops, the concentration starts to drop, ATP starts to go slightly up. But if we then switch on our supply again at the exact value that we had previously, then we're not able to recover the previous high ATP state, but ATP stays low at a very low steady state. So this is a prediction of the model that if you switch off the supply of ATP by some means for some time, ATP high concentration might not be recovered. And we close today's session by showing you at least one experimental result where this was explicitly done. I'll just take all our MATLAB away. So at the final page of your script, you will see where this was done experimentally, a setup in an open flow reaction such that the glycolytic flow through the PFK1 maintained a fairly low ATP level, and that's shown in the central panel that's surrounded by the red frame. In the middle, there was a manipulation, which is something similar to switching the ATP supply off. And when the original setting of the experiment was resumed, where the red arrow goes up again, you can see that the former ATP state is not recovered but remains low. And this is experimental proof of bistability following model simulations previously. And it's, of course, something important to know. And although we don't go into this here, but having the possibility to switch between states is, of course, at the basis of information processing. Switching between 0 and 1, just calling the state 0 and 1, we are immediately to information processing.